I believe many design and analysis methods commonly used in industry contain three major sources of error. In the variability handling approach, each of them is improved through three separate steps. The second source of error is quality assurance for products or data that contain multiple sources of variation. When a product or service contains several variability factors, simply measuring the overall data is not enough. If you only want to understand general trends, a few thousand measurements may be sufficient. But for true quality assurance, instead estimating the full range of variability or the percentage of defects in tens of thousands of measurements may still miss larger variations. This figure shows the variability of the sum of two varying datasets. There are always missing regions near the corners of the data space, and those regions never completely disappear, no matter how much data is added. As the number of variability factors increases from 2 to 3 or 4, the missing regions become even larger. Even millions of measurements may not fully cover the entire variability range. That is why it is necessary to understand each individual source of variation and reflect its distribution information in the overall result. If the variability of each component is measured individually, even a relatively small dataset on 1000 samples can still capture the distribution accurately. And when that distribution information is properly reflected in the overall calculation, the quality guaranteed at the component level can be carried over to the final system. The variability handling approach provides a calculation framework for doing exactly that. As explained in Part 1, the variability handling approach uses distributions that closely reproduce the real shape of actual data. Then, in the second step, instead of using only calculated result data or mixed data containing multiple variability factors, it calculates the exact result distribution directly from the distributions of each individual variability factor. This allows the probability information in each distribution to be reflected accurately in the final result. In the third and final step, relationships between multiple distributions are evaluated using distribution-based metrics, allowing probabilistically rigorous decisions. By doing this, we can achieve much more accurate decisions in many kinds of design and analysis. At the same time, it also opens up many new possibilities for advanced calculations and analysis methods.